Okay, so we're going to start chapter 14 and take a little bit of a different approach as to how we can get more information about the motion of a particle. We're really going to start to look more from the point of view of energy and work, and so you might be familiar with this. We've done this in general physics, and we'll just step it up a notch to do that. I think this picture of a roller coaster is a really good application of how we might be able to use the ideas of conservation of energy, which is going to be in this chapter, maybe work done by gravity, etc. You might remember we've talked about, what about the roller coaster if it goes around the loop and it's upside down, how fast does it have to go in order to not lose contact with the track? So those are the types of questions that we might be looking at as we use work and energy as an approach. Another example here you might have recognized from driving on the highway is you might see these barrels sometimes close to a ramp or close to a barrier that you wouldn't want to run into with your car. And think about how the purpose of those barrels is to really slow the car down so that if you do end up hitting the barrier, you won't be going as fast and hopefully won't be hurt as badly when you do hit the barrier. Or maybe you should just slow down. So first of all, we're going to think about work and energy. So one of the things that this is really just summarizing some of the things that we're going to look at throughout this chapter. In the previous chapter we did F equals ma, and mostly we looked at expressions for acceleration. We might have integrated with respect to time. We'll see that if we write acceleration, rewrite it using the chain rule so that it is equal to v times dv ds, that you can rewrite F equals ma and you actually can derive an expression known as the principle of work and energy. Sometimes in class I think I called it the work kinetic energy theorem, one that's not used a lot. We're also going to look at power, which is the rate of doing work. But you can see that there's a bit of a concentration on the idea of work moving forward, so let's make sure that we understand work. So here's a particle that's moving along a path, and there's a force acting on it, and so we want to find the work done on the object as it goes from position 1, which is at S1, to position 2, which is given by S2. One of the things we got to get used to is some of the notation that we see is a little bit different from what we've used in general physics. So we're going to indicate U is how we express work, and the work done, if you remember, is the dot product of the force with the displacement. Now we're using the integral form right now because this allows for the possibility of either the force changing over the path or the orientation of the force relative to the displacement. Of course, and we would be going from position 1 to position 2. Because this is a dot product, we could also write this as F cosine of theta times ds. You can see that theta is the angle between, right here, the angle between the force and the displacement, which would of course be parallel or tangent to the path that we see there. Also notice that if we think about it this way, F cosine theta is what we might think of as the parallel component. Oh, I don't really need to rewrite. Well, I could write it as component, sorry. The parallel component of the force. And when I say parallel, I mean parallel to the displacement, because that's the only component of force that's going to do the work. We can break down the force into its parallel component and its perpendicular component, but this one doesn't do work because only is perpendicular to the direction of motion, and so it doesn't actually help the object move from point 1 to point 2. And so that's part of the reason that we write work as a dot product, is because it allows us to only include the component of the force that's parallel to the displacement. And so here we see some of the expressions that I already wrote. This is the more general expression for work, where we allow for the possibility of displacement, the displacement and the force changing their orientation to each other so that the angle might change. It also allows for the possibility of the force changing. You can simplify this and get rid of the integral sign if the force and the angle are constant, and then it's simply just the force times the cosine times the displacement, which is this delta S, which is S2 minus S1. If a force is parallel to the displacement, then you do positive work. If the force tends to be at an angle greater than 90 degrees, then it's actually working against the motion, and so that's going to do negative work. Any forces that are perpendicular to the displacement don't do any work. So let's think about some examples of work done by some forces that we're familiar with. And I want you to try to sort of keep these expressions that we derive in your head, because we'll want to circle back to them eventually and think about how they're related to another quantity. So if I want to do the work done by gravity as our object moves from point 1 to point 2, it would be equal to the, I shouldn't write it like that, the weight dotted with the displacement. Now, in this case, it might make more sense to write the weight as minus mg in the j-hat direction. And then the ds, if you look here, has an x component and a y component, because as it's moving from point S1 to S2, it's absolutely changing its x-coordinate and its y-coordinate. I mean, technically it looks like it might be changing its z-coordinate as well, but I'm going to skip that because it's not going to play a factor anyway. If we think about our dot product, we'll see that this doesn't really contribute at all, because the displacement in the x direction is perpendicular to the force. So that any displacement in that direction, gravity didn't help at all. And what we're left with is just minus mg times dy. And then we would go from y1 to y2. And that would be the work done by gravity in going from point 1 to point 2. If we integrate this, it'll be mgy evaluated at y1 and y2, which will give us minus mg y2 minus a minus mg y1, which we could write as minus y2 plus mg y1, or we could write the work done by gravity in going from point 1 to point 2 could be mg y1 minus mg y2. And I am asking you to remember this just because the order of these will have some significance when we talk about potential energy. And here's just the result. Also, we want to look at the work done by a spring, where the force due to a spring is minus ks. We're going to measure, we're going to call the displacement from the equilibrium position our s. So the work in going from S1 to S2. So this is fully one-dimensional, so I'm just going to write it as ks ds, minus ks, sorry. I wrote that, but I didn't say it. And as we do our integration, we can find the work done in moving the object from point 1 to point 2. And what I want you to sort of notice is the original point ends up coming first in these expressions, where the ending point comes second. Traditionally, when we find a change in something, it's final minus initial. And again, like I said, that's going to have some importance when we think about potential energy. Okay, so another idea that we said was going to be investigated in this chapter was a rewriting of F equals ma. Acceleration is the derivative of velocity with respect to time, but I think back in chapter 12 we saw that we could use the chain rule to rewrite this. And what we do essentially is we eliminate time and rewrite acceleration in terms of velocity and position. So if we write F equals ma as mv dv ds, we can then integrate by multiplying both sides by ds. And now we've really successfully separated our variables. But notice that the left-hand side is really just the work in going from point 1 to point 2, because it's F ds, S1 to S2. And then we can relate it to this integral involving velocity. And so let's look at what that is. That would give us mv squared over 2, I evaluated at v1 and v2, which is 1/2 m v2 squared minus 1/2 m v1 squared, which is equal to the change in t, again with the new symbols, where t is how they talk about kinetic energy in this chapter. So basically we find that the work is equal to the change in the kinetic energy. You probably remember that from general physics. That was an important theorem that we learned about. Our book tends to sort of restate this a little bit. Instead of saying the total work is equal to the change in the kinetic energy, which would be T2 minus T1, they express it in a way that is kind of nice if you think about it. Like if they say, if I start with some original kinetic energy and then I do some work on the system, I'm going to be inputting energy into the system, and that will result in a new final kinetic energy. Now, one of the things that we like about using work and energy is that these are quantities that are scalar. Of course, when we calculate work, we do work with vectors, but then the end result is a scalar. And so sometimes working with scalar quantities makes things just a little bit easier. It also turns out, if you haven't realized it, that both kinetic energy and work will have to have the same units, otherwise they couldn't be equal to each other or mixed in an equation. And that unit is the joules, is called joules, and so you should know that. In our system of energy, where a system of units where we use feet and pounds and everything, the unit of energy is a foot-pound. Now, of course, if you talk about forces that are perpendicular to the path, they're not going to do any work, and so that's not going to be useful in those situations. We can also look at a system of particles and apply the work kinetic energy theorem to it by looking at the total value of all the kinetic energies added together and then all the work done by all the forces added together. So the expression will look the same, it's just that you're summing over all the particles. Now, the last thing that we want to look at for this first part of chapter 14 is friction, because friction is kind of weird, and so we have to be careful with how we talk about it. So let's imagine a scenario where a body is being slid over a surface, but it is rough, so there's some applied force we're calling P, and it's being opposed by some friction because the surface is rough. That's code for we got to deal with friction. If we say that the object moves at a constant velocity, then it has to be true that the forces in the x direction add up to be 0. So the applied force P and the frictional force, which is mu times the normal, are going to have to be equal to each other. Now, if we want to use the work-energy theorem, we would probably say we start off with some initial kinetic energy, and then we're going to add the work done by the applied force, and then we have the frictional force, presumably doing some work, and that equals 1/2 mv2 squared. But v1 equals v2 for our example. And that also seems to make sense because we just made the point that P and friction are equal to each other. But what we want to talk about is what's going on right here. Because when we write mu minus mu k normal times s, we're sort of implying that this is the distance through which friction is acting. And that's actually not quite appropriate. Here's a model of sort of the two surfaces interacting, and that's what's causing friction. And so it is possible that these interfaces, there is going to be deformation. And part of the reason that, as those two surfaces rub up against each other and there's, deformation and things break off, that's part of the reason that the friction is present. So it actually is true that there's a distance s prime, and that's the distance that the friction acts through. And s prime is less than s. So you might ask, okay, well then what happens to the distance s minus s prime? What is that? And that is going to go to heat. So the friction does act for some distance, and so the work done by friction I could write as minus mu k normal s prime. And so altogether, the expression mu k n s actually represents the work of the friction plus the energy that's lost to heat. And that's one of the things you might remember is that, for friction, we talk about the fact that some energy is lost to heat. And so that expression that we had in that expression, we have to be careful and not think about it so literally that friction is acting through the same distance that the applied force did. It doesn't really, because of the nature of friction itself. And that expression actually indicates both the work done by friction for a shorter path than the path that P acted through, but it also is including some of the internal energy of the system that got dissipated by heat. All right, so that's it for part 1.